Let's look at example 6, deriving the general formula. Now, this is again, the logistic differential equation, and we're going to see what the solutions will look like. We're going to derive what the solutions should look like. Now, I have completed that already. I wrote it all out in great detail, and that's going to be on Google Classroom. Please look at that. In this one, they're going to make big jumps. They're going to go through the derivation, but they're going to go through big jumps that you might not understand. What I've provided online is very detailed and very comprehensive. So take a look at it. All right, so here's what we're starting with. And we're going to use separation of variables to get it to a solution. The reason you see all this writing here is that I actually did this video and then the computer crashed. And so I'm redoing it. I'm not rewriting every single thing again. So pay attention here. We start with the dy dt. And you'll notice that first thing they do is they're going to multiply both sides by dt. You'll see it cancel out here and it ends up over here. I get k times dt. Because I have a y in this term, I'm going to divide both sides by that. It's going to divide out here, and you end up with 1 over y times quantity 1 minus y over L dy, and that equals k dt. I'm going to take the integral of both sides, and a big step is happening between these two steps here. You'll notice that it goes from this to this, and they tell you that they rewrote it using partial fractions. Well, I hope you remember partial fractions from math analysis. If you don't, I did another write-up on partial fractions, pretty extensive. And if you didn't see it in math analysis, or if you've completely forgotten about it, again, I show you exactly what it is, how to do it, and the different cases. I've taken considerable time to prepare that for you. So please, please, please take a look at those PDF attachments that I've included. So anyway, I went from here to here using partial fractions, and then I'll continue from here. When I take the derivative, when I integrate, both sides, you'll notice I have here, I'll write it. I'm doing this. Okay, and that leads me to this step here. The integral of 1 over y is ln absolute value of y. And if you do a u substitution, you can see how they get this negative sign here for the other part. On the right side, you had just k, and then you end up with kt, and then plus that constant. Now, something that happens here, notice how this was positive, positive, and this was negative. Well, that was a minus sign right here. What they've done is this. They have multiplied every single term by a negative. And so I end up with negative ln absolute value of y plus ln of L minus y equals negative kt minus c. That's what you're seeing here. And taking these two, notice they're both ln's, they're both logs. And if I think of it as ln of absolute value of L minus y minus ln of y, well, I can combine those two together to give me this. Now I'm going to do this to both sides. This is gone, leaving me this. And then over here, I get e to the negative kt, and then times e to the negative c. That's what you're seeing here. So convince yourself that this is equal to this. And then E is a constant, and it's being raised to a constant. So it's going to be a constant. Instead of calling that E to the negative C, we're going to just call it B. And I go from here to here. So how did that happen? Well, it happened like this. I am going to rewrite this. These are two fractions with a common denominator that are being subtracted. L over y minus y over y. Y over y is 1. I'm going to add 1 to both sides, and I get L over y is equal to 1 plus be to the negative kt. I'm going to multiply both sides by y and divide both sides by 1 plus be to the negative kt. And I end up with this, where the L that you see here, that is the carrying capacity. So this is what our solutions are going to look like. And every problem we solve, you're going to see this form. So look for it.